we will go over linear algebra today, and we'll go over 3 problems. Our first, and all 3 of them will be dealing with a system of linear equations, but our first problem will be 1 solution, our next problem will be infinite solutions, and then our last problem will be no solution. Okay? We will begin with our sample systems of linear equations here. So we have 2x2 minus 6x3 equals 2, x1 plus x2 plus x3 equals 1, and 3x1 plus 6x2 minus 5x3 equals 4. Okay, so where do we even begin with this? Well, the first step is to take all of the coefficients that we see here. First, we'll add this here, 0, x1. All right, this is important because we want to make sure that all of the variables are present. And this is important because I'll just reiterate. We want to make sure that all of the variables are present in this case, right? Every single variable needs to be present because you can't have empty. You cannot have an empty. You cannot have an empty cell, we'll say, in a matrix. Alright, so we'll make what's called a coefficient matrix. We'll take each coefficient and we'll put it into well, we have 3 equations here and we have 3 variables, so this will be a 3 by 3 coefficient matrix. So we have 0, 2, 6, 1, 1, 1, and 3, 6, 2, negative 6, and then negative 5. Okay, so this is our coefficient matrix. So, what we need to do is we actually need to convert this into what's called an augmented matrix. Our augmented matrix will have an extra column, alright? An extra column, we'll separate it with a line like this. An extra column that includes the answer to each equation. So this will be 2, 1, and 4. So this is the augmented matrix. We had a coefficient matrix, we set up the coefficient matrix, and then we augmented it so that it included the solutions. Alright? Now what we need to do is we need to do what is called row operations. And we'll start off with elementary row operations. Okay? So there are 3 elementary row operations we can do. We can do row interchanging, we can do row addition, and we can do we can do multiplication by a scalar being just some value, not a matrix, it's just some value. And we do this to each row, not to the entire matrix, but to each row separately. Alright, so when we create an equal matrix, we'll say that, alright, so where do we start? We'll say, alright, where do we start here? Well, we want to put this into what is known as echelon form. And in echelon form, we have what is called a leading term. We want to have that leading term here. And then we have some point underneath that, and to the right, there's another leading term and another leading term. Okay? And those are ones. We want to put this into that. But then what we want to go from there is we want to put this into row reduced echelon form, which would mean that, in fact, we just have a 1, and this would be a pivot point. And then we have pivot columns, which means that any elements above and below are zeros. Okay? So I will go through this one just so that you get the hang of how this actually works visually, of course. So the first thing that we're going to do is, because in echelon form we cannot have a 0 as a leading term, right? The leading term is the first non-zero term in the row, right? we're going to swap row 1 and 2. All right, so we've swapped row 1 and 2, and we've gotten this. 1, 1, 1, 0, negative 6, 2, 3, 6, negative 5, and of course we have the augmented solutions right here. So this is our leading term for the first row. This will be our leading term for the next row. So then this has to be the leading term for the third row. Okay, and why is that? Well, it has to be down and to the right. And because there's no fourth column, right, this is the solutions, we can't do anything with that. We completely ignore this. Oh, it's 2, negative 6, my bad. Hold up, 2, negative 6, negative 5. All right, so we ignore these, right? You can't have this be a leading term because this is part of the augmented coefficient matrix. And what we're trying to do is we're trying to get it so that we get each variable defined. Or we can get it to either a basic variable or a free variable, and we'll get into basic versus free in a little bit. All right. So we want this one to be the leading, this one to be the leading, and this one to be the leading. All right. So in that case, what is the operation that we want to do here? First thing I'll do is I'll move this over here. Okay. 1, 1, 1. 0, 2, negative 6, 1, 2, 4, 3, 6, negative 5. Okay, so what is it that we want to do next? Well, we want this one to be a leading term, right? But in a reduced echelon form, it needs to be a 1. The leading term needs to be a 1. So in that case, we see that 2, negative 6, and 2 all share a common factor, 2. So we can multiply this row by a scalar, and that scalar will be 1/2. All right? So we're multiplying this second row, we're multiplying row 2 by a scalar 1/2. So we go 1, 1, 1, 1, and then 0, 1, negative 3, and then 1. All right. So we've already done row 1. We've already done the operation on that. We're good there, which was the interchange. And then now we've done row 2. So now we want to manipulate row 3. What are we going to do with row 3? Well, we want this to be the pivot right here. And there's no common factor here, so we can't multiply by some scalar. What we can do is we can do row addition. So we'll add this row. We'll add 1 times row 3. We'll add 1 times row 3 by 5 times row 1. All right? Actually, let's not worry about making it that would actually make it a 0. We don't want to do that. We'll do 1 times row 3 by negative 3 times row 1. All right? So what would we get then? Well, we'd get 3 plus negative 3 times 1, so that's 0. 6 times negative 3 times 1, so that's 3. Negative 5 plus negative 3 times 1, that's negative 8. And then 4 times negative 1, 4 times 1 times negative 3, 4 plus 1 times negative 3, my bad, and we get 1. We've ended up with 1, 1, 1 in our solutions. Don't worry about that. That's just a coincidence. And so we've ended up with this as our new augmented matrix. We will change it accordingly here so we can perform our next few operations. So the next thing we want to do is we want to get rid of this value, this 3, right here. We want this to be the leading term, meaning that everything before that in the row has to be a 0. Okay? This is the first, we want this we want this position right here to be the first non-zero term in this row. Alright, so we'll do that first. So we can do 1 times row 3 plus -3 times row 2. So that and gets us 0 plus -3 times 0 is 0. 3 plus -3 times 1 is 0. And -8 plus 3 times -3, that's -3 times -3. So that's -8 plus 9, so that's 1. And then we end up with 1 there, 1 there, right there. So now I will just move everything over as well, because now we are in echelon form. This is our echelon form. We have a non-zero leading term at the start here, right? And it just so happens that they're all ones, so it will be easier to put everything into echelon form. But now that everything is in, now that everything here, right, it's all in echelon form. This is an echelon form. And why is this an echelon form? Well, it's an echelon form because this is the leading term here, this is the leading term here, and this is the leading term here. You see, we can't have this here, right? This isn't an echelon form. Why is this not an echelon form? Well, because this is our leading term for the second row. So because this is our leading term for the second row, we cannot have a non-zero term below it at all. It has to be a 0 below it. Alright, so you see it like this. There has to be a 0 underneath each leading term, unless there's no row underneath it. But you see, there's a 0 here and there's a 0 here. So it has to be like that. There's a 0 here, and then there's nothing underneath here. But in row reduced echelon form, there's no 0 on top of it either. In echelon form, there are only zeros below that leading term. But in row reduced echelon form, we want every single term that is above or below those leading terms to be zeros. Alright, so we'll transfer this. I forgot to do this one. 1 plus -3 times 1 is -2. Alright, so now we are in echelon form. Now we want to go into row reduced echelon form so we can get our solutions. Alright? So we have this. So what are we going to do first? Well, we want this. Well, this one is already a pivot column. Pivot column meaning that this is the pivot point. This is the pivot point here, this 1. And everything above and below it is a 0. So that would be a pivot column. Here, we need to make this a pivot column, and how can we do that? Well, we can do row 1 minus row 2, or basically row 1 plus -1 times row 2. So that's 1 plus -1 times 0, so that's 1. 1 plus -1 times 1 is 0. And then that's 1 plus -1 times 3, so that is 4. 1 plus -1 times 1, and that is 0. Okay, now we have 0, 1, -3, 1. What are we, and so now this is like this. Right, like that. Alright, so this is what the new one would look like. But we also want to make this one, this -3. We also want to make that a 0 as well. So how are we going to do that? We'll leave this bottom one because it's already good. We don't need to do anything with it. Right, we already have 1 there. There's nothing we need to do here. So what is it we're going to do? Well, this is also going to always stay 0 no matter what, except for if we add it to the top row, so let's leave that empty. Let's leave this completely empty. So we have our row 1 and row 3. So what are we going to do with this row 2? We want to get this -3 to a 0. Well, to get that -3 to a 0, we can either add 3 times the row 1, or 3 times row 3. If we add 3 times row 1, what happens is we end up adding 1 plus 0, 0 plus 1 here, so we would get 1, 1 plus 1 here, and we would get 2, and then -3 plus 1 there, right? We can't do that. So what would happen, let's just move this over here, so we get 0, 4, 0. I'll leave this empty. Like that. This will be easier to take care of. Let's do each step. Let's do it step by step, all right? So, 1, 0, 4, 0, 1, -3. All right, so what we're going to do with this -3? Well, we can either we can do some multiply by a scalar and then add the top row, or we can just add 3 times the bottom row, times row 3. If we add this one at all, what happens is we end up getting 0 plus 1, or 0 plus some multiple of 1, and we get a non-zero term there, which makes this the leading term for that row, which we don't want. We want this to stay 0. So in order for this to stay 0, we can only add the row below, so that 0 stays 0. We'll leave this. So we'll add so we'll do row 2 plus 3 times row 3. So that's 0 plus 0, that's 0. That's 1 plus 3 times 0, so that's 1. And then -3 plus 3 times 1, we get 0. And then 1 plus -3 times -2, that's 1 plus 6, that's 7. All right. Now we just have this one term left. And as soon as we get rid of that term, we will be in row reduced echelon form. Now, how do we do this? Remember, we want to make sure that when we're adding the rows, that we end up with this as we don't want this become anything other than 0. So what does that mean? It means that we can only add this to a row that has a 0 in the position here, right? We want this 0 here, the second 0, to stay 0. So which row do we add it? And we want this 1 to stay 1 as well. So we have to add a row with a 0 in the first row, first column, and a 0 in the second column. So that would be the third row, all right? So we'll do this plus -4 times the bottom row. And why -4 times the bottom row? Because 4 plus -4 is 0. So we'll do 1 plus -4 times 0, so that's 1. 0 plus -4 times 0, that's 0. 4 plus -4 times 1, that's 0. 0 plus -4 times -2, that's 0 plus 8, so that's 8. And then we just continue with each row, 0, 0, 1, 7, and -2. Okay, so we have 8. So this is our row reduced echelon form, or RREF matrix. And so this is an RREF because, as you can see, this is our leading term, this is our leading term, and this is our leading term. And below and above each leading term, there are only zeros. Now, if there was another column here, right here, this could be like 1, 3, 0, 0, and then this could be 0, 0, 1, 0, 1, 0, 0, 0, like that. Now, why can we do this? Well, because this is still to the right, it's just 2 to the right, and this, right here, doesn't matter. And why is that? Because this is our leading term, and this is our leading term. You can remove this, and it'll be in echelon form. If you can remove a column and it's an echelon form. Right? Like that. So this is 3, 0, 0. Basically, you can have anything between these two, and then there can be any number on top, as long as there is no numbers as long as there's only zeros on the top and bottom of each leading term, and each leading term has to be a 1. Now, if we let's take this Rref, augmented matrix, and let's rewrite this equation. Well, we're left with 1x1, so that's just x1, plus 0 and 0, so these are gone. And we're left with equals 8. So we have x1 plus 0, x2 plus 8 right there, right? Okay, and then we have 0, 1, and 0, so this is gone, and that's equal to 7. And then both of these are gone, this is 1, and then this is equal to -2. So what are we left with? We're left with x1 equals 8, x2 equals 7, and x3 equals -2. This is a unique solution to that problem. And so that means that x1 has to be equal to 8, x2 has to be equal to 7, and x3 has to be equal to -2. And this is our solution to that system of linear equations. Well, we already know that this one's going to yield an infinite solutions, but let's go through the steps to get there, alright? So again, we'll do the same thing we did last time, but this time, because we know how to set up the augmented matrix, we'll just go straight to that. So we'll end up with -3, -5, 36, and then 10, and then -1, 0, because this is a plus 0, x2, and then 7 and 5. And then 1, 1, -10, -4. So, what's the first step we're going to do here? Well, we want this one to be the leading term, right? So, actually, first thing we'll do is we'll see if there's anything we can do based off of greatest common factor for scalar multiplication. For scalar multiplication, but I don't see anything here, so we'll just move on to the next step. So first thing we'll do is, well, I see that there are no leading 0 terms like at the top here, right? So there's no row interchanging needs to be done here. So let's just do row 1 plus -3 times, no, we want this to be 1, right? Actually, because we already have a non-zero leading term here, let's leave this first row alone. Let's move on to the next row. So we want to make this 0 because we don't want this here. Because this has to be 0, this ends up being the leading term, but we have a 3 by 3. So that means that this is going to have the leading term, or it's going to be all zeros at the bottom. So let's swap the second and third row. So -3, -5, 36, 10, and then 1, 1, -10, -4, and -1, 0, 7, and 5. And let's move that over here. We end up with 1, 1, -10, -4, 5, -1, 0, and 7. Alright, so let's do the next step in our process. So the next step is probably going to be where we take this term here, this 1, and we make it 0. How do we do that? Well, let's just add row 3. So we end up with -3, -5, 36, and 10. Add row 3, so row 2 plus row 3, we get 1 plus -1, so that's 0, 1 plus 0, that's 1, -10 plus 7, oh whoops, my bad. Oh yeah, 0, 1, and and then negative 10 plus 7, that's negative 3, negative 4 plus 5, that's 1. And then negative 1, 0, 7, and 5. So now let's move that change over here. 0, 1, negative 3, and 1. So then what's the next step going to be? Well, our next step will most likely be we want to get this to be a 0. How do we do that? Well, we would add 3 times the top row. Because add negative, well, we would do 3 times row 3 plus negative 3 times row 3 plus row 1. Let's do that. Let's actually do that first. So negative 1. So negative 1 times negative 3 is 3 plus negative 3, 0. 0 times anything is 0 plus negative 5, negative 5. 7 times negative 3 is negative 21. Negative 21 plus 36 is 15. And then 5 times negative 3 is negative 15 plus 10, negative 5. And then I see that we can, there's a common factor here, so we can actually divide this by, let's see, negative 5. So we end up with 1, negative 3, and 1. And now let's do the rest of the rows. Uh-oh, look at this. I see that we have 2 rows that are the same. And you know what that means when we have 2 rows that are the same? It means that they're parallel. Now, it certainly doesn't look like they're parallel here. Like it's negative x1 plus 0, x2 plus 7x3 equals 5, and x1 plus x2 minus 10x3 is negative 4. Right? Those don't look parallel. But if we do these, we end up with the same row. And if you end up with the same row, what happens is that if you do any addition here, which you're going to have to end up doing, because, well, you're going to have to end up doing, right? Because we want this 1 here to be a 0. Because we want this to be the leading term. So let's actually do that right now. We want this one right here, to be a 0. Because we want this to be our leading term. Because we cannot have a leading term, a leading non-zero term, right, to be we do not want that to be underneath another leading term. You cannot have a leading term underneath a leading term, as I went over before. So we want that to be 0. So in order to do that, well, we can't do the first row, any operation with the first row, because then we're going to end up with this 0 being a number, and that defeats the purpose of having done those operations in the first place. So we have to do row 3 plus negative 1 times row 2 in order to cancel out that. So we end up with negative 3, negative 5, 36, and 10, and then 0, 1, negative 3, and 1, and then 0 plus negative 1 times 0 is 0, 1 plus negative 1 times 1 is 0, and negative 3 plus negative 1 times negative 3 is negative 3 plus 3, which is 0, and then 1 plus negative 1 times 1 is 0. So we've ended up with this right here. We've ended up with a row that is fully zeros. There's no leading term anywhere here at all. It's just saying 0 is equal to 0. So this row actually goes away because it doesn't matter, right? This row completely doesn't matter anymore. And because this row doesn't matter, you know what that means? It means we now have more unknowns, more variables, than we do rows. And when you have more rows than you do variables, when you have more variables than you do rows, it means that you're going to have to end up with a free variable. A variable that does not have a value, does not have a set value. Because it doesn't have a set value, you can define it as however you want, because it's free. It doesn't matter what the value is, you're always going to end up with a solution to the problem, That variable is extraneous. Now, let's move that over here. 0, 0, 0, and 0. Let's get this into RREF. So, next step, we want this to be 1. How do we do that? Well, divide by -3. Divide by -3 because we can't add anything to it to get it to that point. So we're going to have to divide by -3. Well, I guess the first thing we can do is we can actually make this 0 so that it's just nicer so we don't get a fraction, right? So let's do that. So let's make this 0 first, I guess. 1 plus, so in order to do that, we would do row 1 plus 5 times row 2. That's -3 plus 5 times 0, that's -3. -5 times 5 times row plus 5 times 1 is 0. 36 plus 5 times -3, that's 36 plus -15. 36 minus 15 is 21. And then 10 plus 5 times 1 is 15. And then we end up with 0, 1, -3, 1, and then 0, 0, 0, and 0. And we'll move this over there. 0, 21, and 15. This will be a lot nicer because now we have a greatest common factor, and that is 3. But let's make this 1, right? So we'll divide by -3. So we end up with 1. 0 divided by -3. Well, we're multiplying by -1/3, not dividing. You multiply by a scalar. But I digress. So 0 times -1/3 is 0. 21 times -1/3, -7. 15 times -1/3, -5. All right, so let's do that because we're going to leave all the other rows the same. So we might as well just move this over here. All right, so what's our next step going to be? Well, our next step is going to be that we want, well, since now we're in echelon form, right? We're echelon form, leading term, leading term. There's no leading terms here, so this row doesn't actually matter. So pretty much we don't have to worry about that bottom row because it doesn't do anything for us. It's just 0 equals 0. But we have this right here, which is keeping us from being in a row reduced echelon form. And because this doesn't have a leading term anywhere here, right? These are the only two leading terms. We don't actually need to make this -3 a 0. And why is that? Because there's no leading term for any row in this column. You can only make every other term in that column 0 if there is a leading term for some row in that column. Like if there was like 2 here, then we would have to make this -3 0. But we don't actually have to do that here. We don't even have to make this -7 0 either, because this is our Rref. And why is that? Because we have 2 leading terms. 2 leading terms. Here and here. And they're both 1. So we have 2 non-zero leading terms that are equal to 1, and above and below those 2 leading terms are zeros. So this doesn't matter. Everything else doesn't matter. We're in our Rref there. So now that we're in our Rref, let's write our new equation out. So we'll end up with x1, that becomes 0, and then -7, x3, and is equal to -5. All right, and then we have this is 0, this becomes 1, and then we have this becomes -3, and this is 1. And this is 0 equals 0. So what do you see that is common between both of these? Well, because we had one more column than we did rows, and we only had this row, this x1 had a defined pivot column, and this x2 had a pivot column, but this x3 didn't have a pivot column. Because it didn't have a pivot column, there's no way to decipher the value of x3, so the value of x3 doesn't actually matter, right? So there are actually infinite solutions to this problem, because it's x1 is equal to -5. Let's put this in terms of the basic variables. So the basic variables are variables that are defined. They have a defined value. A free variable is a variable that is in a row that is not defined. You see how we erased that one completely, that's why. So we end up with x1 is equal to 7x3 minus 5, and then x2 is equal to 3x3 plus 1. And even if we were to define x3, it would just be in terms of x1 and x2, so it doesn't matter. There's no way to actually solve for x3. So what we do in that case is we say x3 is equal to free. It's a free variable because no matter what value we input for, because what happens is that no matter what value we give in for x3, there's some value for x1 and x2 that is a solution to this problem. So basically, whenever you have this right here, you have a row that is full of zeros, or you have more unknowns, more variables than you do equations, or than you do rows, you are most likely going to have an infinite solution. I cannot guarantee it because I have not seen a case so far, but case against what I've said so far. But we'll say that it is most likely going to be an infinite solution if there is a zero here. Well, we already know this is going to end up with no solution, but let's get to that point. Well, we have this plus, let's make that matrix 1, 1, 1, 2, 0, this is 0x1, and then 1, negative 3, 1, and then 2, 1, 5, and 0. First thing we want to do is, well, we already see that this is 0, 1, negative 3. So the first row doesn't have any zeros at the start, and that's good because otherwise we'd have to do row exchange. And in this case, I don't believe we have to do row exchange yet. So we'll leave this first row alone. Second row, well, this is already good, but we want to get rid of this one, right? This 2. So we want to get rid of this 2 here and this 1 here because they're supposed to be zeros. They're only supposed to be zeros below that leading term in an echelon form. And we're going to put this in echelon form and then into row reduced echelon form. Alright, so how are we going to get this 2 to be 0? Well, we would do row 3 plus negative 2 times row 1. And that would be, because that would be 2 plus negative 2 times 1, that would be 0. So let's put that there. 0, and let's leave the first 2 rows the same. Alright, and now let's do this. So then that's 1 times 1. That's 1 times negative 2 times 1, so that's 1 plus negative 2, so that's negative 1. And then 5 plus negative 2 times 1, that's 5 plus negative 2, that's 3. And then we have 0 plus negative 2 times 2, so that's negative 2 times 2 is 4, plus 0, that's 4. Boom, like that. Alright, well now we want to get rid of this one. We want to get rid of this negative 1. So let's actually just add that to this new matrix here. Empty this matrix here. And there we go. So now we're left with this. Alright. So how do we get this negative 1 here, this 1, to be a 0? Well, we can add 1 times row 2. Not 1 times row 3, even though that would make this a 0, right? But this would make this 1, and then we'd have to get rid of that again, right? That defeats the purpose of having it. We only want to add something that will keep this 0 and make this 0. So that'll be 1 times row 2. So that's row 2 plus row 3. So that's negative 1 times 1, negative 1 plus 1, sorry. So that is 0, so well, we already have that 0 there. And then 3 plus negative 3 is 0, and 4 plus 1 is 5. 0, 1, negative 3, 1, 1, 1, 1, 2. Uh-oh, I see a problem here. Doesn't this say that 0 is equal to 5? Is 0 equal to 5? No, it's not, of course. It's not. 0 is not equal to 5, so we can automatically say that this is false. And there is absolutely nothing we can do here because we're saying that there is a leading term here. If there were a 0 here, sure, this would be an infinite solutions. But I'll prove it to you that there are no solutions, right? You're probably like, wait, do some more row operations, see if it ends up, fixing itself. All right, well, let's see if that is true. So we end up with 0, 0, and 0, right? Let's see if that's true. If it in fact is possible, if it in fact will give us a solution. You doubt me. Well, there's no pivot column here, but there's a value here, right? So what are we going to do here? Well, let's just make this in Rref, right? This coefficient matrix is already in echelon form. Okay? The coefficient matrix. Ignore this augmented part. This coefficient matrix is in echelon form. So what are we going to do? Let's get this into Rref. So let's get rid of this 1 because it's supposed to be 0. This is the leading term. We need this to be 0. No leading term in this column here. Alright, so we can leave these alone. So let's make this 0. What do we do? Add -1 times row 2. So we get 1 plus 0 is 1, and 1 plus -1 times 1 is 0. 1 plus -1 times -3 is 1 plus 3, which is 4. 2 plus -1 times 1 is 2 minus 1, which is 1. And then we end up with 0, 1, -3, 1, 0, 0, 0, and 5. So I do recommend that even if you do get something like this, you continue to solve it out. But now we're already in Rref, right? So since we're already in Rref, what that means is these are our solutions. This 0 is equal to 5, right? These are solutions. We end up with this. So it's somewhat similar to the infinite solutions, right? We end up with x1 plus 4x3 is equal to 1. We end up with x2 minus 3x3 equals 1. And we end up with, but at the bottom, instead of saying x3 is free, right, we end up with 0 is equal to 5. And is 0 equal to 5? No, it's not equal to 5, so we know that this is false. There is no solution to this problem because there is a false statement here. All right? If you end up with something like this, if you have 0, 0, 0, and then this last row ends up being a non-zero, in this augmented part of the matrix, if this ends up being a non-zero, and you have zeros in the rest of the row, it's most likely, I'm going to say most likely because I've never seen an opposing matrix, but I'm going to say most likely just in case I'm wrong. Most likely going to be no solution. And so there are your 3 ways, or 3 different solutions to this problem. So you can either get a unique solution, you can get an infinite solution, or you can get a no solution. And I believe there is a way to get multiple unique solutions without it being infinite solution, but this is a basic overview of the topic, and I hope that you now have a good understanding of how to do row reduction and solving linear systems of linear equations.